are being administered in the first place, right? So this is a real life example of something like that. So you have 3 exams. You try to understand how does the class actually do. Rebecca, okay, when you done?
Yeah.
Good, perfect. All right. So you essentially want to really understand where does your class stand, how well are they performing, what's the over distribution, was the quiz too hard, was the quiz too easy. You try to understand that. And so this example really means to kind of illustrate that. So you basically count all entries in the respective groups. You count the proportions in the group. So you create this group and this becomes a grouped frequency table with these different groups. You count the entries in that group of score. You calculate the proportion of the overall set. You calculate averages and standard deviations. And then you basically put this all together in a table. And once you have that in a table, you're basically submitting that as problem 1. You also create a bar chart showing the respective frequencies. Simple. It's not going to be hard. We have done that in class, so you have the guidance in the lecture notes. I did start, yeah. Second example, again, real life example, simplified, and it's not the best example, but it's an example as you could hypothetically quantify to understand at what price, if you sell shirts, at what price will you make the greatest income? And so you would hypothetically do that, also deduct the cost for manufacturing. So this is, it's not the most real life example, but this is kind of along the lines how you would do controlling and planning the conduction of a business. Yes, please.
Like, does each of them need 3 frequency tables, or it's just overall?
No, it would be 1 table for each exam. So you do 1 exam and you can merge them all together. So it's all male and female with count, proportions, percentage, no percentage, average, and standard deviation.
So 1 for each exam.
Yes, and 1 for each gender and all. So it's a little bit of counting. You can set up the actual, you can either set up the count or you just count it. What is important, please, averages and standard deviation. I would please like to see the actual calculation. So calculation of the sum of squares, calculation of the variance. I want to see that calculation, and I would need to take points if I don't see it, because I explicitly ask for it. So this is not me torturing you with this for any other reason, but I want to see that you know how to do those calculations, because I just think it's important for the understanding of these matrices moving forward. So this will only be for this first homework. Second homework, you need to use the functions. For this one, please use the calculations. Okay, entrepreneur prices, same story. You do the group frequency tables. You have the ranges right here, 10 to 14, 15 to 19, 20 to 24. I made it simpler. I simplified this example. Actually, I did less groups, less data. So it's a little bit simpler now. But again, all the calculations, please. You also do scatter plots and bar charts. We know how to do that, simple. Problem number 3 is basically the calculation of the development of a frequency table. Again, we're stratifying in the assembly time of a kitchen unit, and we're basically counting how long each respective employee took to assemble that. And then we're counting within a certain time range. We have a count of employees that took a certain amount of time. That's our count. Then we calculate as a fraction of the overall number of employees, and then we're calculating averages, standard deviations, and and then we're presenting it in a table. Then we develop a scatter plot, relationship between time and age. And then we have 2 more scatter plots for male and females. I also want you to interpret what you see on the scatter plot. It's simple. It's not terrible. Will take a little bit of time, but gets you a good head start into Excel. Should be fun to make. Okay, Any questions concerning the homework? Yes. Excuse me, what?
We're supposed to show the equations.
Yes, the calculations.
So
Each
it's
of,
like,
so the deviations, the squared deviations, the sum of squares, the variance. So each step in between. Yeah. All right. Sure. Okay. Yes.
but just to follow up on that, what if you just plugged in the equation using the formulas? Like you would have to write a formula.
Well, if you only do functions, you lose points. I think last time I took 15 points. It was more points. Maybe like 10-ish, 15-ish points. By calculating each step of the calculation of an average and each step. No, you do it in Excel, but with the calculations.
Right.
Yeah. Okay. But yes,
You
please.
like can't use the Excel formulas, like I can't like click like the formula for standard deviation and plug in my numbers or not,
Well, you can do it, but then you lose points.
but then I lose points.
Yeah.
How do you?
Yeah, it's a little bit tedious, but the calculations are important. Yes.
Can you go over how to do it then?
You want me to do the homework?
No.
Well, we did it. Yeah.
Okay.
No, we did the calculations. We did the calculation. If no, you do it in Excel.
But
Well, the lecture recording of last class shows you how to calculate standard deviation. You
Right,
just
so-
do the same. No, you can. No, you don't use the function. I showed you how to use a function, and I showed you how to calculate it. I want to see the calculations.
Okay.
So each step on the way, so like the deviation, the square deviations, the sum of squares, it's just, it takes you a couple of minutes more.
Okay.
It's not terrible.
Okay.
No, all three. Yeah. Any more questions? I know it's a little annoying, but I want you to see all these steps, and I want you to really kind of like internalize how to do that. And based on my experience, it's a good exercise to do that. Good. Sampling and probability. I want to talk today about sampling and probability. And as said, we're going to go deep into hypothesis testing. So we're going to start off with what hypothesis testing is, why it's important to actually understand what probability is in the context of hypothesis testing, because this is what we will be doing for the rest of this class. We're testing hypothesis. We're calculating the probability of this hypothesis being true or not true. And you will see how that is being done very, very soon. So, but first, let's stay on the basic terms. Samples. We have essentially one high goal, which is to draw a random sample. A random sample is basically a sample where each member of the population has an equal chance to be selected into your sample, into your study sample. So that means that you have an identical representation of your population in your sample. That means you have the same amount of diabetics in there, you have the same amount of people with congestive heart failure, the same amount of people who take blood pressure medication, you have the same amount of people of the same age, you have the same amount, the same distribution of gender, same distribution of race, ethnicity, religion, socioeconomic factors, you name it. Everything should be represented in your sample. Obviously, this is virtually not possible. So what you in most cases are dealing with is a convenience sample or some form of biased sample, unfortunately. So you have, with a convenience sample, you have a sample that is accessible to you, readily available, can be college student. So if you want to understand the happiness in the US population, and you take a survey and you ask everybody in the class and you ask all your colleagues, there's not necessarily a representation of the US population, right? If you go, I don't know, I don't want to use any brand names, but you go in a mall or in a shopping center somewhere close by, this may not be a representation of the US population when you sample 100 people there. So it is a convenient sample because it's for you accessible. It's readily available. People are willing to do the study, or people are just geographically close to you, geographical proximity. So that comes at a price, which is a limited generalizability of your insights. And we'll talk about that in a second. So random sample, every member of the population has an equal chance to be selected in the study. They are almost never used, not because social sciences don't want to, but it's just hard to do. It's difficult to access the whole population and which to select the sample. Even census data sometimes is biased, and there are analytical ways around it that is used for the so-called enhanced study. You basically you look into strata, so you create units of a map, and you find random samples within that unit on the map, and you kind of try to find random representation within the geographic unit. It's analytically quite a tough one, but there are ways around it which are very advanced and very sophisticated. But it is possible to kind of deal with it in some shape or form. So the convenient sample is a sample that uses participants who are readily available. So why would you use convenient sample instead of full random sampling? It's easier, it's cheaper, it's feasible, it's geographically easier, it's logistically easier, organizationally easier. So whatever falls into that ballpark. So the convenient sample comes at a price, and this price is generalizability. Not only generalizability of your sample population, but also generalizability in terms of your ability to apply the findings that you have drawn from your sample to the overall population. If you remember in chapter 1, we compared employees that were part of a wellness program and exercised and the exercise behaviors, and those that were not part of the wellness programs and the exercise behavior. If you have not, that's kind of changed it a little bit. Let's say people that exercise and the level of happiness, and people that don't exercise and the level of happiness. Let's take these two, it's easier. So if you have now a very selected group of young athletic students, you will find a different insight than when you do the study in the US population, or you do it in a nursing home, right? Makes sense. So again, it's about this representation and this association between your sample and the overall population that you're essentially interested in to gain an insight for. So generalizability is also labeled so-called external validity. External validity and generalizability are synonyms. They can be used interchangeably. External validity is in contradistinction, and is basically the brother of internal validity. Internal validity is the validity of the methods that you have used and the way you have analyzed your data, with details to be discussed later on. If you have limited generalizability, what will you do first? Let's say you studied your exercise study, you studied that in a sample which you're not sure is generalizable. What's the logical next step? You study a second sample, right? Or you have somebody else study that sample, or you initiate at the conference, you initiate a conversation with collaborators, you do a multi-center study, and you study the different places, you do a meta-analysis, and so on and so on. But replication is the foundation of research. Only research that can be replicated in different parts of the world and different population with different, I don't know, different researchers, different analytic methods. Replication is key. You need to find the same insight in different samples with different methods, etc., etc. So a convenient sample is also created with what is labeled here so-called volunteer sample. We have talked about volunteer samples with the wellness program and the effect on exercise regimen. A self-selective sample is just, unfortunately, not necessarily generalizable to a population. If you have, for example, you want a survey to be conducted in the US population, and you do either crowdsourcing or online network sampling. With crowdsourcing, you look for a platform where you have a maximized outreach to the community, to the US population. and you ask random people, or you ask people generally like, okay, so here's my survey, please everybody fill it out. You get a certain number of submissions. The problem will be that the people that fill out that survey, that's a very distinct group. That's not a group representative of the US population, where a large fraction doesn't use the internet, or many people don't go on these platforms. So there are various reasons that creates a convenience sample for that approach. Even worse so was the so-called MTurk. Yes. Preferable. Yeah. So crowdsourcing is becoming increasingly popular for various reasons, because it gives you a lot of insight. Also, the online network sampling, the MTurk, you do get you get a signal. You get kind of an idea where people stand in their opinions towards X, Y, Z, but it is biased, and you need to be clear about that this is biased. Surveys like that are done quite frequently, right? It's like you get surveys for, I don't know, you stay in a hotel, or you fly with a plane, you get surveys, right? So there are definitely ways, and I guess a review after taking a plane qualifies as crowdsourcing, because you're trying to get input from a population, which is the plane flyers that fly with, I don't know, with that particular airline. You try to get from the crowd a feedback on how was our service. So that qualifies as crowdsourcing. Excuse me. If you pay for it, as was MTurk, you have you have more accentuated bias in there. The only thing you really need to keep in mind when it comes to biases is this. It's not only do you have a very distinct sample, you also have what is called biased sampling, and you have a testimonial bias. Because testimonials are only filled out by people that do have a certain opinions. So think about the testimonial. Who will fill out the testimonial for a nail polish? That's essentially either the person who is like absolutely in love with that nail polish and think it's the nail polish in the world, the best nail polish in the world, or is the person who really disliked it and is like just angry that you paid that amount of money for that. So there is definitely bias. So the middle field, the middle ground, that is like, yeah, okay, nail polish, but not that great, will not go and write a testimonial. So there's a bias there that is explained essentially by the outcome of that testimonial or that survey. And the same applies with crowdsourcing. When an airline asks for an opinion on the service, same problem applies. Where they try to mitigate this is basically they try different psychological algorithms and approaches to like make it super easy for you that it pops up on an app and you just have to click a star. That gives you a little bit of a less biased response on your service because it doesn't take much time. But reviews and testimonials, they are biased. They are to be treated cautiously. Yeah, so there are various psychological approaches how you would approach this, and yeah, it's gotten better. So nowadays you're not just rating on customer service, you also try to phrase the questions in a way that you give a more unbiased response. So that was random sampling. So random sampling is important because you want a random sample that is representative of the population. So when you think of two different groups, so we have the exercise group and the non-exercise group, and their association with in terms of happiness. If you can, for example, say, okay, so there's a research coordinator, so you go and recruit all the patients for the intervention group, all the participants of the intervention group. And you tell the other research coordinator, you only select now patients, randomly select patients for the non-intervention group. So that would be random selection. I have never seen a study doing it that way. The other way of doing that, no prospective research. The other way this is usually done is so-called random assignment. What's the difference? The difference is that you go and have a research coordinator go and recruit subjects into your study. When you have somebody sign a consent form and participate in a study, you recruited the patient or you recruited the subject, the study subject. Random assignment would be the subject agrees to participate, signs the consent form, then he becomes subject 17, 13. So he gets a subject number, and there is beforehand, there was a random assignment that 1 is intervention group, 2 is control group, 3 is control group, 4 is intervention group. So there is beforehand a randomization scheme which is not known by the person consenting that individual, because that would bias that individual. So this is done beforehand, and usually it's in a sealed envelope. You hand this to the coordinator and you say, okay, recruit the patient, patient signs or subject signs, and then you open the envelope for patient 14 and you say like, ta-da, you're in the control group. That's kind of how this is done. That's how serious this is being considered in research. So random selection is almost never used. Random assignment is frequently used because with random assignment, you minimize confounding and you minimize disbalance of various factors between the two groups, between control and intervention, that will likely change the insights you're gaining from your study. Any questions on random assignment, random sampling? It's not complicated. It's just concepts that are very important to be kept in mind. So probability. Why is probability important? So probability is basically an estimate of an event, and the estimate of a probability of an event occurring rather than not occurring. So it's basically the likelihood of an event to occur out of all possible outcomes of a trial, of an attempt. So when you think of the simplest examples, you have like a die, and you roll a die, and you wanna roll a 6. Your probability is 1/6. If you roll the die 2 times, what's the probability of the second time rolling a 6? Correct. It doesn't change. It's the same, which has been labeled as the so-called gambler's fallacy. Different context. So if you think of a roulette table in Las Vegas, they display the numbers that came over the last 20 times. And you hear at the table discussions between gamblers. It's like, so now it was like red 10 times in a row. The next number has to be a black one. It's like other rubbish, because it's mutually exclusive independent events. It has nothing to do with the previous times. Yes.
Have you heard of the two envelope paradox?
Envelope paradox,
It's
no?
like an exchange paradox. It's about two envelopes with cap. I'll show you after class. It's a probability paradox. I think you'll like it.
Okay, sounds interesting. Yes, please do. Okay, yes, so probability, so this is independence between two events is super important. If the second event is affected by the first event, you have a particular case that we will briefly discuss in a later class, which is you will need to use Bayes' theorem to quantify a conditional probability, which is conditional to the first event to happen. But that's outside of the scope of this class at this point. Good. Okay, so probability, we know now how to quantify probability. It's basically success over the number of trials. So you have the success of a 6 being rolled is 1 over 6 different outcomes. If you go out and you basically, okay, let's say the prevalence or the prevalence is the proportion of a population that has a certain condition, a certain disease. Let's say the prevalence of diabetes in New York City is 10%. If I go out and I randomly pick one individual on the street what's the probability that individual is a diabetic? 1/10, right? It's 10%. So if I sample 1,000 people, how many diabetics will I have? Likely somewhere in the ballpark. It's 1/10 multiplied by 1,000. So this is 100 diabetics. And this is the most important thing for my world. It's the so-called expected relative frequency probability. And there is the association between probability and the relative frequency of a sample. And this is also which is important for random sampling, because if I randomly sample 100 people, the number of people with a certain condition should be representative of that prevalence or probability, that proportion in the overall population. So that goes in both directions. And so this is called that trial. So that's the individual picked individual in my sample. Outcome would be diabetes, yes, no. Success is my 1/10 becomes 100 diabetics out of my sample of 1,000. And when this probability translates into a frequency of a certain condition in my sample, this is the so-called law of large numbers. If I let's do the thought experiment a little further, because it becomes even more interesting. Because if you do, let's say you draw, okay, we stick with diabetes 10%. You're picking 100 people, and you pick those 100 times. What will happen? You get, so with a probability of 10% of picking a diabetic, you will have in a sample of 100, you will have more or less around 10 individuals. But it's not going to be 10 individuals with each time you draw a sample. So it actually will be sample 1 is 7, sample 2 is 12, sample 3 is 9, sample 4 is 10. So it will have an estimate somewhere around 10. If you do that at 100 times or 1,000 times, you get a beautiful normal distribution around 10. And that is why you can use the principle of normal distribution to the case where you have a binary outcome, either diabetic or non-diabetic. You basically get that frequency, that expected relative frequency probability represented in the distribution around that actual proportion in the population. So the more often you are drawing, the more accurate your estimate of the population prevalence will be. And that is actually very useful to know, because keeping that in mind, that opens the door for hypothesis testing, as we will do it, because that probability that we're comparing now is based on exactly that principle. Okay, any questions on this? So obviously the expected relative frequency probability is different from the personal probability, which is essentially a subjective probability. And there is the probability where I say, I give it like 20% on home before 8. So it's a certain estimate, which is usually not really based on, I have observed my behavior over the last four years of teaching at yeshiva. I know there's a 20% probability I will be home. And so it's a subjective probability. I'm just saying this to estimate some form of probability. Yes.
That's independence and probability.
Hmm?
That's independence and probability.
Well, no, that's subjective probability. That's subjective, and it kind of goes hand in hand with confirmation bias, where like, I knew it, it's only 20%. So it goes in that direction. So the personal biases and the personal probabilities, they're kind of like, yeah, they're related in a way. So confirmation biases, for example, where you have a preconceived notion, and then you see this reflected in an event to happen or not, and you find yourself confirmed, and you basically get confidence about your confirmed notion. That's a confirmation bias. It goes hand in hand. Illusionary correlation is, so I'm wearing the talisman I don't know, the talisman of my grandmother, and I'm running 3 minutes fast on a marathon. So it's something that is not there, but I assume it's there because I'm seeing it happening. So these are the biases that people apply to probabilities. So personal subjective probability, expected relative frequency, and then we have law of large numbers we discussed. Independence of probability. Independence is what is explained before with the conditional probability. So if I have a preceding event affecting the probability of an event in a second line, this is a conditional probability. And then these events are not independent. In many cases, however, they are independent from each other. So that's independence of events, mutually exclusive events. Okay, probability of success over trials, we talked about that, and confidence. Confidence is important. So confidence is the personal probability that is a rating of our confidence that a certain event will occur. We will talk about confidence. So this is the confidence of the person based on the personal probability. But now we have confidence can also be an interpretation of a calculated probability, and we will discuss that in chapter 9, no, chapter 8. Chapter 8, when we talk about confidence intervals, because they are basically used also for hypothesis testing, where you can ascertain a certain event to be true with the confidence based on this calculated probability. And we will calculate this and discuss this in chapter 8. So confidence is basically the confidence into a certain condition or a certain event to be true.
Wait, isn't that the p-value? Like, doesn't that have to do with p-value?
It does have to do with p-value, yeah. So you're right. If you have a p-value so the p, yeah. Okay, we're jumping ahead a bit. So the p-value is essentially the confidence that an event will not be true.
Right. So if you have 95% confidence, you have 5% p-value.
If you have a 95% confidence, or a confidence interval, you're 95% certain that the population mean will be in that interval. 5% you're certain it's not in there.
That's the p-value.
Well, the p-value is the probability.
Okay.
The p-value stands for, it's a probability value. Where it's getting interesting is that p-value that you consider your alpha. And we will get there in 3 slides to the alpha, because the alpha determines the risk or the acceptable risk of a type 1 error. But we'll get there. Very good point. Okay, rules of probability to test hypothesis. So we essentially are testing hypothesis. If I say, okay, I'm testing now exercise and happiness. So I have a group that does not exercise and I have a group that does exercise. So how happy is that group? How happy is that group on a scale from 1 to 5? I get 100 responses from that group, 100 responses from that group. I compare all the responses in terms of their means. And now I want to have some form of probability that are these actually different? So the means are different, but am I actually sure that this is different? And that's why I'm using the probability of this difference that I see in the means actually being true or not. So that is the p-value. Is that difference actually real? Real, yeah, true, correct. So you use this probability to make decisions whether 2 groups are quote unquote significantly different from each other. So you basically, you determine whether means are significantly different from each other, and you do that by probabilities. If I come to the conclusion that they're not significantly different, then they're basically from the same distribution and they do not differ from each other. And that's just due to some sampling error or pure chance. The means are actually slightly different, but they're basically not significantly different. And the inference is that there's no difference between those 2 groups. And for that reason, we need to be able to develop hypotheses. And these hypotheses basically evolve around one primary hypothesis, and that is the null hypothesis. And that means that the null hypothesis is basically the ground truth where I'm saying people that exercise are not happier compared to people that don't exercise. So with the null hypothesis, I assume null effect of my intervention. And so there's no difference between those two groups. I mean to test this hypothesis, and see whether there's a certain probability that actually the null hypothesis may be not correct, but actually the research hypothesis may be correct. And that can only be done if the probability of the null hypothesis being correct is less than 5%. Then I assume the null hypothesis to be false, and I reject the null hypothesis at a quote-unquote alpha level of 5%. And that would be the p-value. So always keep in mind, the simplest way how to look at this is with a control group and the experimental group, where the control group receives the treatment and the experimental group does not receive the treatment. The experimental group does receive the treatment. That's the simplest example. So null hypothesis, research hypothesis. Null hypothesis is being tested. If the probability for that being true is less than 5%, you reject the null hypothesis. You accept the research hypothesis. So that's what's written on this slide. So you reject null hypothesis, there's a difference. You fail to reject, there's no difference.
You say you accept the alternate hypothesis.
You can say that too, but as said, your null hypothesis is the ground truth. You're accepting that there's no difference. That's the angle you're looking at this. And that is conceptually quite important, because that's where a lot of people trip over that concept. Sometimes it's very important, sometimes it's not important. Let's put it that way. But the definition is important because it needs to be a universal definition, and this is generally what the research community embraces. You will hear an interesting talk from a very fascinating researcher, Cassie Kosikov, decision. She's the decision lead for Google Analytics. Very fascinating person. She will talk about decision making, why it's important to basically look at hypothesis testing and decision making and the way it's being looked at. I hope you will like that discussion for the entry. Very fascinating lecture series she had. Hypothesis testing. Okay, so we said null hypothesis, no change or difference. We fail to reject the null hypothesis, then we assume this null hypothesis to be true. Research hypothesis, there is a change or a difference, and I reject the null hypothesis, and the research hypothesis is supported. And the key to your question, if research hypothesis is supported, you still don't 100% know your alternative hypothesis is correct.
Do you ever 100% know anything?
No. That's the beauty of research. You never know with 100%. There is no certainty. That's the interesting thing about research. There will never be certainty. And well, is there actually ever a certainty? No, there's no certainty at all. Heisenberg has formulated that in the 19th century. Yeah, there's no certainty, right? Or the black cat Schrödinger's cat. So, okay, so we have type 1 and type 2 errors. So, and this is also the angle why you're looking at the null hypothesis is so important, because you have a type 1 and the type 2 error. So the type 1 error is when you're rejecting a null hypothesis that you shouldn't have rejected. Yeah, I like the reactions. Okay. Yeah, it's so, and this is why the angle matters, because you assume under the null hypothesis there's no change. And I come to the conclusion that I reject the null hypothesis at a level at a probability less than 5%. So I'm like not certain this is actually true. So it's less likely true than it is not true. But there's still a rest error that I'm making the wrong conclusion, and that I think there's a difference where there is actually no difference. And that little rest risk is the type 1 error. This will all make sense. I see the skeptical looks and I understand, but it will all make sense. And then you have the next error is the type 2 error, where you fail to reject the null hypothesis when it is false and when it should be rejected. So now to put this in context, let's assume a researcher has like this fabulous blood pressure medication that lowers the blood pressure and has the potential to lower cardiovascular risk for a large fraction of the population, as the claim. The NIH gives $50 million to the researcher to study this blood pressure medication. So now we're coming out and we see the null hypothesis to be rejected with a p-value less than 5%, but there was some subsetting, and maybe there's a confounder that kind of sneaked in. It could be a type 1 error. And you're basically assuming now that that blood pressure medication is actually super effective and super efficient. And you make a conclusion and you gain an insight with ramifications of an entire population to which you will prescribe this medication now, thinking that it's super effective. So it really means to kind of protect the population from gaining insights that actually shouldn't be gained. So knowing that type 1 error, being transparent in your research, showing all potential confounders, knowing exactly what was supposed to be studied, is that transparency that drives research. And that's why it's important to understand that there is the risk of a type 1 error. What causes type 1 errors? And often it's confounding and it's subsetting, and there are certain things that can lead to that. And it is just important to understand how to identify that in analysis. So now let's take the same blood pressure medication. Again, the NIH gave $50 million. We have a type 2 error. What's the outcome if the null hypothesis is not rejected, although it shouldn't have been rejected? You wasted $50 million because you didn't do proper quote unquote power calculation, because that's how you determine and that's how you minimize the risk of a type 2 error by doing a so-called power calculation, where you estimate how many people do you need to study to get an insight that is solid and powered at, bless you, at least 90% statistical power. So the statistical power is basically a resultant of 100% determining it's wrong, it's right. That's 100%. It's a binary outcome. The type 2 error shouldn't exceed 10%. So it's 1 minus 10 leads to the statistical power. So that's actually your confidence in the insights that you have gained. So the type 2 error is where you're not rejecting what you should have rejected. And that's a design error in many cases. All right, and there's a shocking prevalence of type 1 errors, and that comes back to my statement earlier. It's like, yeah, you did subsetting, you introduced a confounder that kind of now made your results lean in one direction versus the other. That's a type 1 error, and there is, according to Norton and Heinzen, and there's a shocking prevalence of type 1 errors, meaning that there are many studies that suffer from type 1 errors. Whether this means they're all flawed and they're all really type 1 errors, that is not me to decide, but I would say many studies are basically kind of aiming to see significant differences because it's easier to publish those. And that makes it a little tricky, because then you sometimes may be tempted to do subsets that you shouldn't have done, subsets that led to some confounding. I shy away from generalizations, but I'm just generalizing. It's not impossible that there are a shocking high prevalence of type 1 errors. So yeah, it's definitely, so there are some certain behavior that will more likely yield significant results. Some of them may be type 1 errors. Let's put it up. That was diplomatic enough. Good. That's this. All right, that's all I had lecture-wise, but we have something else. And we have an R code. Please download R code module 7 from Canvas. And I really want to show you this one because it is module 7 sampling.r, yes. And what we're doing in this code is something that hopefully will kind of make it a little bit more illustrative what we have been discussing and what we will be discussing in the next class, because we will be talking about the association between sample and population and the association between sample mean and population mean, which is connected with the so-called central limit theorem. But more about that next class. So what we're doing here first, can you all see this? So please, those of you that go along, if you click on packages, there is the button install, and install allows you to install packages. If you click here, AIMS housing, AMES housing, this allows you to install the package that line number 1 is basically calling with library AIMS housing. Yes, please install it. Yeah. If you just click here and install, I'm not reinstalling it here, you just install it quickly. And once there's like a lot of crazy stuff happening there on the left lower side, don't worry, no, don't. I see like panics in your eyes. It's like nothing happens, nothing happens. You have an error. Error is not good. Error is not good.
AMES, like what is it called?
AIMS, AMES, AMES housing. And this is Ames, Iowa. And that is a distribution of all the houses in Ames, Iowa. It's a pretty cool data set, essentially. So if you click now on library Ames housing, that's line number 1. You basically have now a file called Ames raw in there. And when you just quickly look at these variables, so you have 2,930 houses are being characterized in this database based on the size of the porch, the alley they're in, the size of the bath in the basement, the size of the garage. So you have all this information about all these houses in this database. And there's a reason why I chose this database, because you can now so if you run then line 4, you basically build a subset, or you build a smaller object called Ames, and that only contains 2 different variables. One is house ID and one is the greater living area. And this clearly is not a New York City apartment because that is a living area, a New York City residence stream. So you have like a certain fraction of houses with up to 3,000 square feet. So that's quite remarkable, actually. And if you click on summary, you get a characterization of your population. Yes, please.
Mine's saying errors when I try to run the code.
Which one?
This one.
Did you run this one?
No.
Yeah, you need to run this one first. Did you install the package?
Yeah.
Okay, then just run line 1.
Okay.
And then it should start the package. And then you have this data frame at your disposition. That should work. So what's nice now when you characterize, now you're the variable greater living area. You see here, min, max, 25th, 75th percentile, you see median and mean. So you see the entire distribution mapped out in front of you, and you see on HIST, HIST, you see the distribution of this living area size. So now I want to do a little exercise, and we talked about sampling, right? So we want a random sample, and R allows for you to randomly sample data. If you go on line 14, line 14 creates a sample of your house population of 60 samples. So 60 random samples from house population with replace equals false. You're telling R, do not put that house back in the pool, just take 60 out and don't put them back in. And you get a list of 60 houses that have been randomly sampled. And that's basically nothing else but here. So if you do now a summary of DF1, you see that the mean of 1,431 is considerably smaller than the actual mean. There's like 70 square feet apart, right? So there's a shift to the left. So that sample is not really too representative. Also, min and max are totally off, right? If you click on line 17, you get DF2. You have different numbers. It's random sampling. It's random sampling. If you see different numbers, don't be concerned. It's random sampling. So it's literally different each time you run it. If you run DF2, line 17, you basically, I get here a different sample again. If I have here summary, I get here 1,504. That's actually pretty, that's still off, still off. And now let's take a step back. If I want representativeness of the population, what's going to be the easiest way to get representativeness or better generalizability? Exactly, increase the sample size, because then I get more representation into my sample, right? And so now we have here 1,431, that's like 70 off or 69 off. 1,513, that's not too terrible actually. But if I increase this to 600 and run it now, I basically, okay, that was terrible. Okay, that should be closer to that actually. Okay, this again. So this is 1,429. If we sample this again, so it's gonna be closer to the mean. But that's the power of randomness, right? You basically randomly sample, you can't really 100% predict it. You get a probability it's gonna be closer. But if you increase the sample size, your sample mean will be closer to the sample, to the population mean. So that is the take-home message. That is the take-home message. The more you sample, the closer it's to the population mean, and the skinnier is going to be the distribution. So and the last example that I want to run here, then we can actually soon conclude. It's a shorter lecture today. Line 24 to 30 will basically repeat the same exercise of drawing 60 samples of 60 500 times. So we draw 500 samples. So if you select now line 24 to 30 and compare this distribution to this distribution. Isn't that the nicest normal distribution we have seen so far in this class? So essentially, yes.
So should we run those lines together?
Yes. So so you see a normal distribution of these sample means. So that is a so-called distribution of the sample means. And this is characterized, if you do a distribution of the sample means, that's 500 different means distributing around the true mean of the population, and essentially having a very skinny distribution. And looking at this, that relationship between the distribution of the sample means and the true population mean is called the central limit theorem. And this is what we will discuss next class. So this will come again. So we are from that point on, we're dealing with sample means in a way that we're assuming they're actually the mean of 500 different samples or more, a limitless number of samples. And we will discuss this in more detail next class. Okay, any questions to the R code? Yes. If you want to, yeah. This is just this is not to be submitted. This is not to be submitted. I recommend you try to play around with it and try to understand the different functions. So it's not something you need to submit if that's the question. Sure. Okay. Any questions to any of this? If not, then have a nice evening. See you next week on Monday. Any technical questions? No? Everybody's R works?
My graph looks different.
Well, just try. But this is randomness, right? This is randomness that you will see. Oh, the envelope.
You ever seen this? It's so famous. And like tells you how to solve it. It's like so
This is
basic stuff.
yeah. This is the same as you have the quiz show where you can pick out of three different it's the same. It's the same principle. So you have you remember there was this show with the song where you can like choose one door. No, that was before your time. So you have three different doors and you can pick one door, and behind the door is gonna be the sports car.
Okay.
And you're saying, okay, I want the middle door. And then it's like, okay, so this is sealed in, and then the moderator, the TV show host, turns to you and says, like, are you sure? If you at this point you say, no, I want actually the right one, you actually have a higher probability of getting the sports car. It's the same principle. I like that principle. It's a nice thought experiment. But this is basically because it's not independent events. That is where the trick kicks in. It is somewhat weird. It's so what you may be interested in, and I didn't show this for, in this class. I showed it in the other class.
It's a really famous type